Hello, my name is David Koisser, and it's my pleasure to present to you CER, Efficient Certificate Validation in Constrained Networks. This was a collaboration between the University of California, Irvine, and the Technical University of Darmstadt, where I also work. So our motivation for this work was to enable public key infrastructures in constrained networks. So how are constrained networks defined? Well, for one, they usually consist of devices with anemic computation and storage abilities. This can be, for example, due to strict power budgets. On the other hand, these devices often also have limited bandwidth, which can be, for example, due to long-range, low-power antennas. Then these devices may also experience intermittent connectivity, for example, because they need to hibernate to conserve power. And then there might be also dynamic topology, which simply could be due to moving nodes. So if we want to use trust establishment via a public key infrastructure, it's very hard to do this under these conditions. Specifically, it is hard to check the up-to-date revocation status of certificates. So let's look at some existing revocation checks and why they are not sufficient in this case. So for one, we have the online certificate status protocol, like used in the internet often. So if one node sends a certificate to another node, the verifying node will directly check with the issuing certificate authority if the certificate has been indeed revoked or not. However, this requires a reliable connection to the CA, which might not be always the case, and it also induces expensive communication overhead because all devices in all encounters need to check this. Then we can also do this via certificate revocation lists. Here, the CA will, prior to the encounter, distribute a list of all revocations. Then, if a node sends a certificate, the verifier can simply check the list if the certificate is revoked or not. However, these lists grow quite large, and because they also need to be updated and distributed via the network, also are very heavy on the communication. Then there's kind of a third alternative with a state-of-the-art alternative to lists. So essentially they work like certificate revocation lists. For example, you have CER Lite or Let's Revoke, but they replace the list with a more clever and efficient data structure to reduce the size of the revocation information. However, these approaches still do not handle cases where nodes miss updates well, because nodes need to re-request revocation data. So overall, aside some other issues, the biggest problem here is there's lots of calling home needed, which puts a large demand on the network. So our solution CER proposes a flexible and lightweight revocation check that enables PKI in constrained networks. We do this by epidemic dissemination of validation information, and we define novel algorithms that allow devices to keep each other up to date. Finally, we also evaluated this on a real satellite and implemented a large-scale simulation. So, to outline how CER works, keep in mind this is simplified for brevity, and if you're interested, I encourage you to read the paper. So, if we look at the naive approach of the CER way to do things, if we have a set of active certificates, we can actually represent this as Merkle trees, because we can have the hashes of the certificate and then concatenate these hashes. So we get like a binary tree, and we get a tree root hash that represents all active certificates, which means certificates that are not revoked. So now we can disseminate the tree root hash as the validation information, which can be stored on the verifying node. And then if another node comes, it will have a so-called proof of inclusion, because its certificate is also part of the set, the leaf. And we can take this path and a couple of hashes, which can be sent along with the certificate. And the verifying node can recalculate this path. And if it arrives at the same tree root hash, can prove that this certificate is indeed not revoked. However, this approach, this naive approach, has an obvious problem, because on any changes, for example, if we have a revocation or an issuance, all proofs of inclusion become invalid because the tree changes. So what we do in CER is threefold. For one, we define the validation forest data structure, which I will not go into detail, so you have to see the paper for this. We also use an alternative to the Merkle hash tree called the Sparse Merkle Tree, which gets us a deterministic structure of the hash tree. Then we also define novel distributed repair algorithms that allow up-to-date nodes to help outdated nodes to become up-to-date again. So we leverage the deterministic structure of the Sparse Merkle tree to do this collaborative updating. So to kind of show you how this works, let's consider an example. So we have the certificate authority and a couple of nodes which know the current tree root hash and have their individual proofs of inclusion for their respective certificates. Now, if a certificate got revoked, then the entire tree changes. This, of course, implies that the network gets outdated. So the tree roots are outdated and the individual proofs of inclusion as well. So the CA can distribute such an update with a new root and a couple of information that allows nodes to update their individual proofs of inclusion. However, a couple of nodes will not receive this update because they're obstructed, hibernating, or similar. So if we simplify the view here a little bit with the updated nodes, and for example, one node moves, it will meet other nodes. And in this case, it can actually share the new root, which is universal for all nodes. And it can also share its up-to-date proof of inclusion, which may allow these nodes to update their own proofs of inclusion. And then, of course, if we have many up-to-date nodes, they may meet some more nodes, and this is where we get this epidemic spread of validation information. So the nice thing about this is that it's topology independent because it only relies on direct contact messages and has a very fast revocation enforcement. So to go into a bit more detail about the distributed repair algorithms, let's quickly talk about the Sparse Merkle tree. So with the Sparse Merkle tree, the idea is to have all possible outputs of the used hash functions as leaves. As you can see here, from 000 to FFF. Now we can build a giant Merkle tree up to its tree root hash. And as you can see, this gets quite big. So the idea here is that most parts of this tree will be empty. And empty parts can be identified and omitted, both in the tree representation as well as in the proofs of inclusion. So we leverage this for our distributed repair of proofs. So here's a simple example. So consider a node with its certificate. It has a deterministic position in the tree because the hash of the certificate defines where it is in the tree, and we know exactly which proofs of inclusion hashes it needs for its proof, and it will store this. Now, if our tree has some changes, for example, as a new issued certificate, parts of the proof of inclusion of our original node will change. So now, if this node meets another up-to-date node, which has its own certificate and proof of inclusion, it can share this proof of inclusion. And because we know exactly, again, the position is deterministic, this allows the original node to calculate its missing hash and thus become up to date again. So one use case that we considered are satellite networks. So why are satellite networks important? Well, for one, the space sector is growing dramatically, which only one of the indicators that you can see here is the number of operational satellites, which is currently growing exponentially and there is no end in sight. And a key trend here is the move towards large networks of small and cheap satellites, opposed to the traditional way of building very big individual ones. So we did an evaluation in space, actually. For this, we collaborated with the European Space Agency, and because they have a CubeSat called OPSAT, which is actually open for anyone to register and upload experiments. And while it's not the most powerful, and we also had to make some concessions on the implementation, we ported our open source proof of concept and deployed it on the satellite and evaluated it on board in space. Then, to show the effectiveness of the distributed repair, we also did a large-scale simulation. So here we simulated up to 1 million nodes, and each day certificate gets revoked and reissued. Each week, fresh certificate gets issued, and each node randomly meets 5 nodes per hour with, of course, a try to distributed repair their proof of inclusion. And also we simulated a share of nodes that miss CA updates. So for the results, if you look at the most extreme result that we have with 1 million nodes and 50% of nodes actually missing the CA update, we can still show that the distributed repair approach avoids 93% of outdated nodes that need to call home to update their revocation information. Then, of course, with this direct exchange of nodes, we also measured how much communication overhead this makes. And in our previously mentioned extreme case, we need actually less than 100 kilobytes of communications overhead per node per week. So, in conclusion, we use a Merkle tree root hash as validation information, which allows a epidemic spread for fast revocation enforcement. Then we use proof of inclusions as the non-revoked proof, and defined novel distributed repair algorithms that allow up-to-date nodes to help outdated nodes, which leads to a probabilistic approach where a large share of outdated nodes can be repaired. And finally, because we only use contact messages, direct contact messages for this, this is all topology independent. So thank you very much, and I'm happy to take questions.